Alright, so the last video talked about one example of exponential growth, and that is our money. And compound interest is an exponential growth formula. Now, in general, if we're just talking about generic exponential growth and decay, then those formulas all fit the same model. When we say exponential growth and decay, here we're talking about continuous growth. With our money, they only put interest in there maybe 4 times in a year, or once or twice in a year. But here, this type of growth, anytime we see the E involved, we know that we're talking about continuous growth. So things like bacteria growing in a petri dish, the population of an island out in the middle of the Pacific, um, the amount of plutonium left if we just let it sit in a lump on the counter for hundreds and thousands of years. Okay, that sort of growth and decay. And we're going to see that letter E in a lot of our formulas, our natural base, and where it came from is situations like this. In nature, as populations grow and decay, this number showed up often enough that they gave it a name. So the pieces of that formula, the y sub 0, and sometimes I'll call it y naught, not a question, but y sub 0, that's our initial amount, our initial population. So maybe it's 1,000 people in our city. Maybe it's 4 grams of plutonium. Maybe our initial population is 100 bacteria spores in the petri dish from the doorknob. K is our growth or decay rate, and we can tell what our population is doing, which of those it's doing, by the sign of K. If K is a positive number, then our population is getting bigger as time goes on. And if K is a negative number, then our population is decaying or getting smaller as time goes on. T in the formula means time, and with interest, we said T always had to be in years. So 4 meant 4 years and 9 meant 9 years. But here time can be in any units, so you just have to read the problem carefully. Sometimes we talk about growth over a decade, and T is in decades. Maybe time is in years, or maybe it's in days or weeks. Maybe you're measuring in hours if you're watching, maybe you're watching bacteria growth in your petri dish. When we start with this much growing or decaying this fast for that long, the y is the amount that we end up with. Okay, so I'm not going to call it the final amount, but the amount after that time. So if we look at an equation, and in most of our problems, not all of them, but most of our problems, they'll give us the growth model or decay model and say, hey, my population is growing according to y equals 200 e to the 0.03t. Okay, and I don't know what this population represents, but we're also told that t is in years. So just from looking at this formula, if we ask a question, what is the initial population? We can peel that out of the formula because it's the coefficient down there on the ground. Okay, so whether this is 200 people or 200 panda bears or 200 grams of plutonium, the initial amount that we're starting with is 200. If we ask the question, what will the population be in 12 years, then we're looking for the y. And that means I'm going to put the 12 years in for the t. And this is just a calculator problem. Okay. So go ahead and pause the video if you want. Ask your calculator this question, and then when you turn it back on, you can see what the population is. Okay, first of all, I had a typo here. Before I paused it, this said 0.3, and it needs to be 0.03 just like it was up in the original equation. So if you ask your calculator 200 e to the 0.03 times 12, you should get 286.7. Yours is not the right thing here because I am getting ahead of myself. Okay, so the population is 286.7 people or grams or bacteria, whatever that represented. So what we're more often going to be answering, the questions that we'll be answering in this section are things like how long. which if it's asking me how long, that means I'm looking for the time. Okay, ignore that question at the bottom. And if I'm solving for time, I'm trying to get to that exponent, which means I'm going to need what? If it asks me how long until the population is 250, 250 is my ending amount. And so if I'm trying to solve for time, I know that, and time is stuck up in the air, I know I'm going to need my logarithms to get that question answered. Now, if we want to start by taking the log of both sides here in this step, I can do that, but it's going to create more steps down the road, and it'll make a mess that most of you won't really know how to clean up. So the first step we're going to do is good, bad, or ugly. We're going to divide both sides by that initial population. Okay, we want to get that exponential term all by itself. So we can either leave it, this is one time because our calculator doesn't care what kind of fraction we type in, whether it's in lowest terms or not. Again, be careful rounding if you do decimals here. This one's a nice decimal that terminates pretty quickly, so feel free to use decimals if you'd like. Now, when we take the log of both sides, we can use, remember, common log or natural log, either one, because our calculator understands both of those. But anytime I see an e in my equation, I'm going to want to pick the natural log. Just thinking back and looking back at what we've learned about our logarithms and their inverses, we know that if the bases match, okay, where the natural log is understood to be base e, and all that remains there is the exponent. So the natural log of e to the 0.03t is just 0.03t. And then I say, well, I know how to solve that for t. Move the next part of the problem out of the way. And I'm going to divide both sides by 0.03. Now, I'm going to tell you that if the problem doesn't tell you to do, to round to something different, rounding to the nearest tenth is okay with me. Okay, if it says round to the nearest hundredth, or if it tells you round to some certain decimal place, then you need to follow those directions, please. But otherwise, since I didn't specify, I just said how long, we'll round to the nearest tenth. T is 7.4. Since we're solving for t this time, I ran out of room to put my units with my answer, but it is 7.4 years. It'll take just over 7 years, almost 7.5, to go from 200 to 250. So then the next question that I ask is to find the doubling time of that population. And the doubling time is what it sounds like. We want to know how much time it takes for the population to double. So in this example here, we're starting with 200. We were given that initial population when we were given the formula. Okay. And that was the first question we answered. We understand that this coefficient here is the initial population. If I want to know how long until the population doubles, that means I want to know how long until the population is equal to 400. Go ahead and pause the video, mimic what we did up here, solving for t. Go ahead and round your time, if you would, to the nearest tenth of a year again. Okay, so divide, use your logs, and then divide again, and round. Alright, first step is to divide both sides by the 200. I need to get that coefficient gone. I have a nice number 2 here, e to the 0.03t. We use natural log of both sides. Again, you can use common log, but then you have to deal with other properties, and it creates more steps. And so just use the natural log here, because then all you're left with is that 0.03t. Natural log of 2 divided by 0.03 leaves you with 23.10490602. So to the nearest tenth, we're going to round that to 23.1 years. In the next video, we'll have more examples.